So welcome to this interaction session. You can ask me. I see only one participant now. You could ask me questions on the course. If you have any conceptual questions, comments, something that you didn't understand, you can ask. On the course on superconductivity. We can speak.
Yes, we can.
The question is that is it possible to cryogenically cool the EV in future to get superconducting and supermagnetism in motor and battery and so on and so forth? This question, see, the thing is that getting a transition temperature for normal superconductors, the ones that we have talked about, is too low, is few Kelvin, like 20 Kelvin or even lesser than that. So 20 Kelvin is like minus, 250 degrees, for example. So minus 250 degrees cooling, and to sustain that cooling, is that possible? That's the question. Because the cooling costs will be much more than the normal, cost to run an EV, for example. So this is at least as of now doesn't look viable. Okay. Google had tried these superconducting chips for the quantum computer that they have had come up with some time back. But that's so those are really at temperature which are of the order of maybe 50, 60 Kelvin. Now, to have a quantum computer in every home, if you need to maintain the your motherboard or the gates, etc., and the chips to be maintained at that temperature, that itself will have a huge cost. Okay? You remember that some of the vaccine-making companies in Europe, they wanted the vaccine to be preserved at very low temperature. However, that would increase the cost of the vaccine, and India is such a big country that taking from one place to another would be such expensive cooling equipment would be a lot of cost. So I don't think at this moment that there's economically viable option. Please do ask me fast. Yes, I mean we can make the efficiency better if you have lower and lower temperatures. So suppose if not superconducting temperature, but some temperature which is much lower than the room temperature, then the performance will definitely be better. See, basically everything is related to Joule loss, okay, heating losses. In Joule loss, if you could minimize it, the performance goes up, the efficiency goes up, and the money that's required to run something. Pawan, yes, I can suggest there is a very nice book by Michael Tinkham on superconductivity. Okay. That you can study, and if you could minimize it, also look at some other efficiency goes up. Ashford Mermin, he has a chapter money that's required to run, I believe. So, but Michael Tinkham is completely yes, devoted to superconductivity. There's an old book which you probably don't get it on market now. It's called DGEN, PG DGEN. DGEN, it's written as DE, then GENNES, a French name. It's a very good book, but I doubt that whether you'll get it in the market. D-wave order symmetry means that it is of the form of cos kx minus cos ky. So the order parameter no longer is uniform in k space, the momentum space. It has some k dependence, and the dependence is of the form of cos kx minus cos ky. Okay, so this is what this the D-wave order symmetry means. If you have that, then you have nodal points. Let me try to sort of explain what I mean. Let me share something. PowerPoint, right? Windows, blank PPT, yeah. Okay, so what I mean by that is it is like that. Okay, so let me just, for my own convenience. So there are terms such as like this and this. So let me draw the Fermi surface. I'm sort of messing it up more. So this is the Fermi surface. Okay, and so there are these nodal points. Now the D-wave order parameter now has gapless points. Okay, so these are gapless points. You see that there are 4 points where you don't need any energy for excitation. The electrons can simply get excited and go to the normal state. So whereas the S wave is just like this. So this is the Fermi surface, and this is the S wave order parameter. This is the Fermi surface, and this is the D wave order parameter. Okay, this is what I mean. So the outer one is the order parameter. In this thing is just the superconducting order. Okay, which when vanishes gives rise to this thing, a normal state. Drawing on the slide is not visible. I'll get some help.
It's fine here. I don't know why they are not filming.
Can you see it now? Writing not visible. Oops. Oh, probably it's in the first slide, is it? Or which I didn't
Yes.
use? Oh,
Yes, maybe.
so you have to delete all the slides.
You can just write
Again,
again.
I can do that.
Just for testing purpose.
Yeah. What happens? I mean, why doesn't it write? It will never like this. You have to take a.
Okay.
So this must be the first page, right? So let me know if you see this. Can you see? Okay, visible now. Okay. This is it's visible now. So what I meant to say is that you have a Fermi surface here, and you have the D wave order parameter, which is like this. Okay. These are the gapless points where excitation is possible without any energy cost. Okay. So these are these nodal lines. And for an ordinary S wave, it is uniform in K space. So it's actually a K space picture. The inner one that you see is the Fermi surface, and the outer one is the SC order parameter. SC means superconducting. Okay. Now please ask if you have any question. What's meant by no thanks? Did you understand it, or I need to explain it once more? Oh, you meant that there's no more question. Okay. Okay, thank you. So again, you asked for a book with starting knowledge that you can get in any book. In fact, a lot of Indian authors' books also have superconductivity. Not that I sort of have anything against those books, but sometimes, it is not very authentic in the sense that it's not very reliable information that's been passed on. I've seen some books which are not very good for even beginners to read, because it's important that you read a very good book in order to understand. So I believe that if you read Tinkham, Tinkham is it has mathematics, but it also has very good writing style. So you can actually have a look at this. Yeah, please ask me. Otherwise, we'll have to wrap up sooner than it was scheduled for. With no more questions, then we'll hold back for only for 5-6 minutes. Of course, one is that getting a room temperature superconductor. So that's probably the highest thing that one can think of. This is what people have been trying for since the beginning, actually. So unfortunately, because the cooling is the main cost, material costs are important, but once you set up a technology, getting that material, if some material becomes superconducting, then getting that material produced is not so economically stressful. But maintaining a temperature lower than the room temperature is taxing. So getting all these superconductors at room temperature is one. Secondly, getting exotic superconductors, I mean, with multiple kind of order parameter symmetries, such as someone asked about D wave. So whether in some regime, parameter regime, whether it has S wave, and in other parameter regime it has D wave, and so on and so forth. So this could be important advancement in terms of research. And the first one that I said would be advancement in terms of commercial use and so on. Okay. The advancement in research will be But whether that can translate to everyday use is something that I'm not too sure. Even, maybe 50 years or even more down the line. No, I mean, in the sense that the whole thing looked like that flower-like thing is d wave because it's cos kx minus cos ky. So if you plot cos kx minus cos ky on top of that circle, which is a Fermi sphere, then it'll look like the one that I had drawn. So it is not about the nodal points, it's about the symmetry of the order parameter. So just try plotting that. You first plot cos kx minus cos ky, and then put a smaller circle in between and see the, the how, where there are gapless points and so on. So it's about the symmetry of the order parameter, not about the gapless points. I mean, those gapless points appear at certain kx, ky value. That is true, but not otherwise. Research, a lot of groups are working all across the world. They are trying to get higher and higher temperature superconductors, ceramic superconductors, newer and newer materials showing superconductivity. So material research is going on, commercial applications is going on, application to the field of medicine is going on, application to the field of computer industry is going on. Many and just the search for materials, like you have the periodic table right in front of you. Okay, how many groups have really been successful in having a superconducting compound? So one needs to understand that what are the different band structures and of different materials that we need to combine with, and how we should combine at what proportions so that we have a particular kind of electronic dispersion. So things are complicated. That's why the research is, think of it, in 1908 it was discovered, and today is 2023. People are still talking about superconductivity. So it's 115 years have gone by, and then we still talk about superconductivity. So it is why it was 1908. That's an interesting story because helium was liquefied on the year before. Okay, so that was the turning point for superconductivity because you need low temperature. So liquid helium gives you temperature which is about 4 Kelvin, 4.2 Kelvin. Yes, a lot of research. I told you some of them. There could be many more. Thank you. Yeah. Okay. Second order perturbation theory. Let me go to the slide. I hope you can see the slide. Is the slide visible? Okay. So second order perturbation theory means that you have a perturbation term, and then you are not satisfied with the first order result. Not sure. No, it says yes.
No, sir, but it's not visible actually.
Not visible.
So whatever you are writing is not visible, sir.
Oh, okay, okay. You do it.
So,
Just wait for a moment. Oh, you are to that small. Oh, okay, okay. So, yeah, so the first order, but I can't write with this environment, right? That's it.
give me the pen, sir.
No. No, it doesn't write. It only writes in the full screen mode. Now it will write. Last paragraph. Yeah. Oh, you have to every time you have to do this. I don't know what is its problem. Yeah, I think you can see it. So not clear. Not at all clear. My assistant says that it's not clear, but let me know. So this is the first order result, where you take the expectation value of the Hamiltonian. The Hamiltonian means the perturbation term. So your H is equal to H0 plus H prime. H prime is the perturbation term, and H0 is the original Hamiltonian. The solutions to Suman, that I don't know. In this type of this, okay. It's not coming at all. Okay, let me at least write if you can see it good, but otherwise. So this requires an intermediate step as well. So it's a psi n h prime psi m and psi m h prime psi n divided by En minus Em. That's the result for the second order perturbation theory. Now, what you do is you do a perturbation theory to believing that the eigenstates of the original Hamiltonian remain good even in presence of the perturbation. Yes, that is what is being said. Just give me some moments.
I don't know why is it me.
Maybe this one is the, so you say. It,
Will it explain it then why it doesn't?
now I have written. So now it can.
Just
It's clear.
one second.
It's clear.
Yes.
Okay, good.
You can explain, sir.
Okay, so this En2 is the second order energy correction due to the perturbation. That's called a second order perturbation theory. Now, when you need that is the question. You need that in a variety of situations. One is that when the first order gives you no information. Okay, that is, it gives you zero information. That is the first order, it is zero. Such as the first order Stark effect in the ground state of the hydrogen atom is zero. The second order then gives you some information. Now this sum over m that you see is an intermediate state that the system goes into and then again relax back to the original state. So it's a psi n h prime psi m, where psi m is again an eigenstate of h naught. Okay. And psi n, psi m, both are eigenstates of h naught. H naught is written on the top. Okay. And En and Em are the corresponding energy denominator. Okay. So this actually, has an energy denominator, and this is what the second order perturbation theory means. And we need it in superconductivity because the formation of Cooper pair, etc. That is, if one wants to explain that, then this is required. How exactly, to electrons which are otherwise repulsive in nature can go on to form a bound pair. Okay, so if you have to understand that, then you have to sort of understand that it first interacts with a lattice excitation, which is called as phonon. And then it relaxes back, giving back an electron. Okay, thank you. Grand canonical ensemble is, what is an ensemble? The ensembles are mental copies of your system. Suppose you have a classical ideal gas, and then you want to do statistical mechanics on that. Now, the statistical mechanics demands not only one copy, but several copies. Okay, so you make mental copies of your system. So as if you have just replicated it, this thing. So suppose you have a coffee cup in your room, and imagine that the room is filled with billions and billions of coffee cups. Each one is an ensemble. Okay? Now, these ensembles can actually exchange energy. Okay, so it can exchange energy. It can exchange particles. That is, it can exchange the whatever the content of the particle, or they may not exchange anything. When these ensembles do not exchange anything, then we call it a microcanonical ensemble. When these ensembles exchange only energy, then we call it a canonical ensemble. And grand canonical is when they exchange both number of particles and energy. Okay, that's called as a grand canonical. The word grand probably because you have relaxed all constraints. Yes, thank you. Okay, we didn't get any more questions, so it's only 10 minutes left. If you still have, you can type it, or if you do not have, then we'll close the session. Okay. So anyway, this is the only interaction session because it's only a 4-week course. If you have any queries, then you could speak to the TAs, and I believe that these PMRF scholars also are there. Yet met one of them. Okay. Yes, what is meant by CK up dagger? The dagger implies creation of a particle. That's CK up dagger. I mean, CK up dagger means creation of an upspin particle with momentum K. Dagger means creation. And without a dagger means annihilation, destruction. So you create a particle or you destroy a particle, that is shown by dagger or without a dagger. Okay, then I think that is.
Thanks.